It usually ramps her up even more.
All right, just watch your chair on that when you back up, not to move the camera, please. All right. Yes. Yeah, yeah, we can. Are those extras? All right. The quizzes from last time should be coming around. And I forgot markers today, so I'm going to hope that some of these work.
They never do.
Yeah. Is that a good one?
Every marker.
It's yours? Haha.
Yeah.
You have access to them, right? Okay, hold on, everyone. If y'all could just be quiet for just a second. Okay, James. James! Hold on, shh, real quick. Okay, all right, never mind. Speak away. Where's my towel? There it is. Okay, we have a lot to do. We have a test a week from today, and it covers topics out of a section we haven't even started. So we want to get to that, but it wouldn't be fair to continue without at least talking about Riemann sums. So Riemann sums, the whole idea behind Riemann sums is just to motivate the idea of where the actual notation for the integral comes from. Copy? The Riemann sums is just to motivate where we get the notation of this from. Because when I first started using this notation, I said, hey, look, like we call this the integral symbol, f of x, dx was the differential. This notation comes from the Riemann sums. So we are going to do some Riemann sums, and you will never have to do them on a test. I'm not going to, so I don't want you to tune out, but I want you to, pay attention, but don't freak out if you're not following it. Okay, before we can actually start, we have to all understand that there are some common sums, some common formulas. I've put this on your desks. Some common sums that we should be aware of. So the notation we use for sums, and the way it came out here, I apologize, the K and the N are kind of offset on the side. Normally I write the K here and N here. Our first one, that's our first common sum formula. All this says is that if you try and take a sum, K equals 1, and we already talked about this notation, right? In class, or no? No, we did not? I thought we did. Okay. Okay, so all this notation means, this is your capital Greek letter S, so sum S, right? And it's just a condensed way of writing something that we want to add up, like if we want to add up a lot of things. So let me give you this example to start. Let me back up a second. If you want to say you want to add, 1 plus 2 plus 3, and you want to do that all the way out to, I don't know what I have here, 120? You don't want to have to write down 1 plus 2 plus 3 all the way out to 120, right? Maybe there's a more condensed way we can write it. So the way we write it is using this sigma notation. We say, okay, we're going to take the sum, and what we're going to do is we're going to have this thing called the starting index. Which is this letter right here. K is a standard letter we use in summations, but you can use other letters like J. It just, it's up to you, really. You just want to stay away from things like X, theta, things that we were using for other things, right? And then up here you have what we call the ending or the stopping point of your index. And then next to the summation you have some expression. And this expression is usually going to involve K. So if I put K here, then what this means is this. It means we're going to start with K being 1. All right? Everyone let K be 1 and write that down. So K is 1, we put 1, right? Then we say plus. And now what we do, and I put plus because this is a sum. Now what we do is we increase K by 1 unit, by exactly one integer. So K was 1, now it's 2. right? So I make it a 2, and then I say, okay, plus. And now I let k go up again. So what is k now? 3. And I'm going to keep doing that, and when am I going to stop? I'm going to stop when I get to n, okay? So do you see how this right here is a condensed way of writing a long string of sums, of additions, yes? So if I wanted to do this, 1 plus 2 plus 3 all the way to 120, then I would write sum, k equals 1 to 120, right? That's where I want to stop. And then here I just put k. All right? You'll see how that's a nice condensed way of writing a big sum? Okay, so what about this? What if you wanted to do this? 2 plus 4 plus 6 plus 8 plus, and you want to just stop, let's say, at 2,248. So this time, we're not doing like 1, then 2, then 3. How much is k going up by each time? 2. Okay, we're still going to start at 1, though. Okay? But our expression in here that involves k should be what? 2k. All right? So that way, when I plug in 1 for k, what do I get? 2. And then I go plus, and then I plug in 2 for k, and I get 2 times 2 is 4. And then I'll plug in 3 for k and get 6. Does that make sense? Yes. Okay, now the question is, where do we stop? 2,000. Sure? 1,124. 1,124. Why? Because as k goes up, we need to stop here, because when we stop here and plug that in here, we get that last one, right? If you stop at 2,248, you're actually going to be way past this endpoint. Does that make sense? Yes. Okay, so yes, and we can put anything we want in here. Okay, does not matter what we put there. In fact, it doesn't even have to. Like this could be 2k squared. It could be 2 times the square root of k. It could be any expression. Sine of k. There's no limitations. You could even put just a constant. And this is the one that's the first one on here. Like what if you wanted to do, let's say you wanted to do, as an example, 4 plus 4 plus 4 plus 4, and let's say you wanted to keep on doing this and end at 4, and let's say you wanted to add up 4, I don't know, 100 times. Right? We all know that that would be 400, yes? 100 4s added up should be 400. But how would this look in sigma notation? Well, sum, k is going to start at 1. Now tell me about the expression in here. 4. In just 4, right? There actually is no k here, because we don't want that to change, do we? It's just 4 each time. So if we put 4 here, then let's just see, let's not worry about the stopping point. Let's just see what would happen first. K is 1, right? K has no impact on this. But we write down whatever we get. What do we get? 4. Okay? Now I say, all right, let k be 2. And write down this again, right? So that's just another 4. And I'm going to keep doing this every single time, let k go up again. And when do I stop? Well, when do I want to stop? When I get 100 of these, right? So what should I put up here? 100. And that should give me 100 4s added together, right? What's the answer? 400. How could you get that answer by just, like, imagine you didn't have this. If you're just looking at this, how could you have gotten 400?
C times n.
C times n. You could just multiply those two together, couldn't you? And that's what the first formula says here. If you ever see a sum where k equals 1, starts at 1 and ends at n, and you have a constant here, c, just a constant with no k in there, then this is just going to be c times n. It's just those two multiplied. Okay? So that's the first common sum. The second common sum, the second one that we should be aware of before we proceed, is what I refer to as the birthday formula, or the spanking formula. I'll explain. Okay, so that's the second important one everyone should be aware of. So let k be 1, right? This is 1, then plus, now k is 2, so 2. Yes? We just did this one a second ago. 3, and where are we stopping? N. Okay, now, the question is, can we figure out what that adds up to be? And there's actually a formula for it. And I'm not going to prove the formula for you, all right, unless we have time at the end, which I doubt. This right here adds up to be what, according to this sheet? N times n plus 1 divided by 2. It's weird. So the example I have here is if you want to take the sum k equals 1 to 120 of k, then this is going to be 1 plus 2 plus 3 all the way out to 120. That's what that means, right? That's what this means. But according to the formula, this should just be equal to what? 1, wherever we stop, right? This is where we stop. That's where we stop. That's n. So it should be n times n plus 1, so add 1 to that, and then divide that by 2. And that comes out to be, what, 7,260. So I call it the birthday function or the spanking function, because if, let's say you live to be 120 years old, this would be, in theory, how many birthday candles you blew out on all your cakes, right? First birthday, you blew out 1 candle. You didn't really blow it out, but you know what I mean. 2 candles, 3 candles. So in your whole life, you died when you were 20 or 120. So this is how many candles you, in theory, would have blown out. Or if you get a spanking for your birthday, right? You get 1 spanking for your first birthday and 2 for your second. This just adds up the spankings, right? Yeah? Okay, so I'm not going to get into this, again, unless we have time at the end of class. It's really kind of cool to see how you can prove that formula is true. But it's very useful, and we need it to do Riemann sums. Questions? The next common formula that we should be aware of is not adding up the first integers, right? 1 plus 2 plus 3, but adding up the squares of the integers. So instead of putting k here, putting k squared. This is 1 squared plus 2 squared plus 3 squared, and you do this all the way out to n squared. So there is a formula for this. The formula is that adds up to be n times n plus 1. Doesn't it look like that so far? Mm-hmm. Yep, one more thing here. 2n plus 1, that's different, yes? And then divide the whole thing by what? 6. Okay, that's very different then. But that's the formula we have if you want to add up the sum of the squares of the integers. So this is just the sum of the integers, and this is the sum of the squares of the first n integers. And then I have a third one here for the sum of the cubes. Y'all see that? Okay. I'm not going to write that one down. All right. We're going to move forward. Remember, I'm going to come back to this. We're going to see it here in a little bit. Yes?
Do you know who invented this thing?
Well, it's not really an invention. It's
Or an observation?
yeah, it's more of an observation. I mean, there's not like some big mathematician who has his name attached to it, you know? If, like, again, I can show you at the end one way you could...
It's not Mr. Common.
No. All right. Here we go. So we're going to go back to the question we had last class. And that is, if you have a function and you're going to try and find the area underneath that curve, then the way we could do it is by adding up the areas of a certain number of rectangles, right? And then the more rectangles we have, the better our approximation will be, right? So we're going to look at a specific example first, and then we're going to try and generalize it. So for this particular example, we are looking at the function. What's in blue here is the function f of x equals x squared. Okay, so we know the blue curve is x squared, all right? And we're only going to be looking on the interval 1 to 5. And we are going to create how many rectangles? This is just, we're just picking a number here. I did 1, 2, 3, 4, 5, 6, 7, 8. So we're going to do it with 8 rectangles. So this is like the method of exhaustion that I talked about with the circle last time. We could sit here and try and calculate the approximate area using 8 rectangles under this curve and add up all those areas, right? So let's go about trying to do that. So let's talk about rectangle. Let's call these rectangle 1, rectangle 2, rectangle 3, so on and so forth. This will be rectangle 8. Yeah? Okay, there's something that all the rectangles have in common. And what is that? How wide they are. Aren't they all, I mean, if I drew them equally, which I am saying we're going to do, okay, then they all have the same width. So how wide is each rectangle? Half. Now how are you getting a half from? Are you just looking and seeing it?
Yes.
Yeah, okay, so how would we get that if we didn't know, like if it didn't look like 1/2? So here's the way you do it. You'd say, all right, what's the distance between here and here, right? So I'm going to write this down. The width of each rectangle would be what? How wide the interval is. So how wide is that interval?
1.
You would go 5 and take away 1. It's 4 units long, isn't it? And then you divide that by however many rectangles you have, which would be what? 8. And that would be 4/8, which is a half. Okay? Do y'all see how I did that? We said, what's the distance between here and here? Okay, and then we said we're going to cut it into 8 equal pieces, so divide it up into 8 equal pieces, and that means that each rectangle will have a width of 1/2. That we agree with? Okay? All right. Now, what if I wanted to find the area? Let's try and find the area, capital A, of the first rectangle. The area of the first rectangle. All right, so what do we already know? It's 1/2 wide, right? It's 1/2 wide. So I know that it's 1/2 times, now we need to know how tall it is, don't we? Okay, so to know how tall it is means that we need to go to the right corner of this rectangle and go up and figure out what that value is, right? That's the height of the function. That's the height of the function at what x coordinate? So do you know that x coordinate? What is it? It's 1 plus a half, right?
Yeah.
So 3/2? Yes? And then you'd have to plug 3/2 into the function to figure out how tall it is, yes? So I'm going to write this down a little bit different. I'm going to say this is our width, right? The height is the function's value at, where? The x coordinate, which we said was 3/2, right? Now I'm going to write it different. I could write 3/2, but I'm not going to. Bear with me, this is going to help us try and generalize this. Would you agree that I could look at this endpoint right here, or this x coordinate, I could look at it as being starting at 1, that's right here, and then moving over by the width of the rectangle. So I could say 1 plus a half. And yes, that's 3/2, yes? Okay, so the area of rectangle 1 is its width times its height. Its width times its height. Got it? Now we could compute this, couldn't we? Okay, I'm not going to, but we could. Let's talk about the area of rectangle 2. Okay, area of rectangle 2. How wide is it? It's 1/2. Okay, times. All right, so now where are we? We're right here, aren't we? And that goes up, and we need to figure out how tall that is. That would be the function's value at that point, which is 2. But again, I'm going to look at it a little different. I'm going to say to get to 2, we would actually have to start at 1 and then move over by how much? 2 1/2. Yes? Again, bear with me, all right? Bear with me. I know it seems weird, but instead of writing the number 2, I'm going to say start at the left end point, 1, and then add to that, I'll do it this way, 2 1/2. I know you're sitting there like, what the? Right? It's like, why are you making this so complicated? Now, if you put this together, what would we get? Half of 2 is 1, and then 1 plus 1 is 2, and that's where we are, right? Okay, let's keep going. Are there any questions at this point? I need to do 8 rectangles this way. Okay, so now, what's rectangle 3 look like? Its area. The area of rectangle 3 is equal to, well, we know its width, right? 1/2. And then times the function's value where? Okay. Yeah, so now we're going to use the same idea. We're going to start here at this left endpoint, and we're going to try and get ourselves to here now. So we've got to go start at 1 and then add by what? How many jumps of a half? 3 jumps of a half this time, right? we're going to go 3 1/2, right? Feel good? All right. And do you see a pattern developing here? Let's see if we can get the fourth one. The area of the fourth rectangle is 1/2. That's never going to change. Function's value at 1 plus what? 4 1/2 this time. And then what would be the area of the fifth rectangle? 1/2. The function evaluated at 1 plus 5, right? I'll write them all down. I may as well, yes? We only have 8 to write, so I got to get rid of that. The area of the fifth one, of the rectangle 5, is 1/2 f of 1 plus 5 1/2. The area of rectangle 6 is 1/2 times the function's value at 1 plus 6 times 1/2. 2 more. The area of rectangle 7 would be equal to 1/2 times the function's value at 1 plus 7 times 1/2. And then the very last one, the area of rectangle 8 should be 1/2 times the function's value at 1 plus 8 times 1/2. Now let's actually figure out what this number is. What's half of 8? 4 plus 1? 5. Was that the right endpoint? It was, wasn't it? So that looks like our formula actually works because the right endpoint is 5. So when we get to the very end, we should get 5 in here. Okay? Now, why is this important? Why are we torturing ourselves doing it this way? Well, would you agree with this? The approximate area. Okay, so I'm just going to say A. Let's put a tilde over it. I'm just going to use a tilde just to say this is not the true area under that curve. It's the approximate area, okay? Would you all agree that the approximate area is just the sum, okay, the sum of k equals 1 to 8 of all of the areas of the rectangles? Okay, look the way I wrote that. Summation, k is going to start at 1 and end at 8, right? What are we adding up? We're adding up the areas of all the rectangles. So the first thing I would do is replace k with 1, and that would be a sub r sub 1. And that would be this one, right? And then plus. Now we'd be at a sub r sub 2. And then plus a sub r sub 3. So do you all agree with that? Okay. But isn't that just the sum k equals 1 to 8? Like, aren't all of these formulas almost identical? What is the only thing in these formulas that's changing? This is the key to the problem right here. What is the only thing changing from 1 to 2 to 3 to 4, 5, 6, 7, 8? What's the only thing changing? The coefficient in front of the half. That number right there, that's a 1 times a half, right? This is 2 times a half. This one was a 3. This one is a 4. This one is a 5. This one is a 6. And this one's 7 and an 8. That's the only thing changing in all the formulas. Everything else in that formula is exactly the same, isn't it? So I could write this. I could write 1/2 f of 1 plus k times a half. Sorry, sometimes I get mad at myself that I try and do all of calculus on this little board, but then I remember Newton did it all in a shed, so I'm like, I think we can handle it. We've got air conditioning and heating at least. All right, so yes? Do y'all see how this would work? If I let k be 1, what would this be? It would be this one, wouldn't it? Then if I let k be 2, I'd say plus, and then if k is 2, I've got this one, and then 3, and then 4, and then 5, and then I'm going to stop at 8, right? Good? Okay, now what can we do with that? I mean, I've got to erase all this, except for where we are. So what we can do now is we can actually ask ourselves, what is this? What is that? So let's just kind of go to the side here and do a little scratch work. If I ask you right now, what is f of 1 plus This right here, I'm going to write a little different. 1/2 k. If I ask you that, can you tell me what that is? Do we know what the function f is that we're working with? It's x squared, isn't it? Isn't the function we're working with right now x squared? Yes. So if you plug something into that function, what does it do to it? It squares it, right? That's all it does. So you can actually tell me what this is. This is just 1 plus 1/2 k squared. See, no more functional notation, because for this specific function, we know what it is, right? It's just squaring the input. And can you square that? Absolutely. You can FOIL that out, right? Okay, so let's square it. 1 plus 1/2 k times 1 plus 1/2 k. And let's just go ahead and do this. And when we do that, we should get 1 plus k plus 1/4 k squared. That's what we should get. Agreed? Isn't this fun?
Now, do we just put n into that?
Nope, because remember, all I've written down here is what's in that red box, right? That's what's in that red box. So I'm going to come back to this now, all right? I'm going to come back to this. I'm going to rewrite it, but I'm going to replace that red box with this. Okay, let's do that up here. So here's where we are. The approximate area, which I'm calling A tilde, is equal to the sum, k equals 1 to 8, of the 1/2 we have in front here, right? That 1/2. And then times this. So in parentheses, 1 plus k plus 1/4 k squared. And what's great about that sum is that it no longer involves f of something, right? Like f was our function, but because of this step, f is gone. It's been evaluated. Now, if we change the curve, right, to a different function, then this is different. Okay, but for this particular example, I just need to add that up. And if I can do this sum, I'm good. Okay, so let's try and do this sum. Okay, watch what I do here. This equals sum, see if you can follow this. K equals 1 to 8, 1/2 plus 1/2 k plus 1/8 k squared. So all I did was distributed the 1/2 through, right? And now, a property of sums, and I didn't get into the property of sums too much or at all because, well, I can just tell you what they are, all right, without us getting too bogged down today. If you have the summation of a bunch of terms being added together, you can split it into separate sums. Okay, that is a property of sums. So long as they're finite sums, like you stop here at 8. Later on we go to infinity, but that's not today. Okay, so if we do this, so you're kind of taking this on faith at this point. Okay, that's where we are now. So that step right there, we're all going to just believe that that's allowed. Okay. So you're just happy. I'm telling you that's okay for us to do. And then there's one more thing that we're allowed to do that I'm going to tell you is okay for finite sums, and that is any constants you have can come out of the sum in front. So my next line is going to look like this. Sum. Bear with me. I'm going to leave that 1/2 there. But on the next one, I'm going to pull the 1/2 out. And on the last one, I'm going to pull the 1/8 out. Not an 8. Okay, any questions on that? You're believing that that's allowed? Does it make sense that it would be allowed?
Yes.
It does?
Yes.
I hope it does.
Again,
It's like the integral. Let me show you a quick little example. If I wanted us to actually do this, okay, if like that's this one, right? Well, actually, that's this one, isn't it? Wouldn't this be 1/2 plus? That's plug in 1, then what? Plug in 2, and you get 1/2 times 2, right? Plus, then you'd have 1/2 times 3, and then plus a half times 4. And all of them would have a half in them, wouldn't they? And so if you factored a half out of all of these, it would now become 1 half. You take a half, so 1 plus 2 plus 3, all the way out until 8, right? But isn't this sum, the sum k equals 1 to 8 of just k? Like, isn't that what this is right here? And then you just have a half in front. So the constant can come out, right? If you understood that, great. If not, just, again, take it on faith for now. Okay, now, anyone know what we're going to do now? These are common sums. This is a common sum. And this one is a common sum. And that one is a common sum. Okay, so let's work on that first one. This first one is like the first common sum here, isn't it? You have a constant here, you don't have a k. So what should the answer to this be? 4. You're getting that by just multiplying this times this, right? So you get 4 there. Plus, now you have a half times, now this right here is a sum of the first 8 integers. This is 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 plus 8, right? And according to the formula, that should turn into what? 8 times 9 over 2. So that's the formula, n times n plus 1 over 2. N is always where we stop. Yes? And then we have plus 1/8, and then what's the formula for this one? K squared, if we stop at 8. 8 times 9 times, now 2n plus 1, so 16 plus 1, 17, all over 6. And I think we can clean this up. This is 4 plus, okay, what can we do here? 2 times 2 is 4, 4 goes into 8 twice, so we should get 18 there on that one. And then on this one, the 8s go away. I can go, 3 goes into here twice, 3 goes in there 3 times. I'm going to leave it as, you want to go 25.5? That's fine. Either way. 25.5, get a decimal. We're approximating anyway, right? So 25.5. And now add them all up. What do you get if you add them all up? 47.5. That is our approximate area using 8 rectangles. Yes? Now I had the computer do it for me, and it got the same thing. 47.5. Yes?
It's probably more difficult, more accurate, but on where the line is, the triangles on the left, could you calculate those and then slide a line on the bottom of it to make a right triangle there? And then you calculate the area of the rectangles underneath it.
So you could go and try different shapes. There's actually different methods. We were using, like I told you, let's make these rectangles and let's go make this first rectangle and go to the right end point and go up, right? You don't have to do that. You could have used the left end points. Let me show you, because I have it right here. I can use the left end points. How would it change if we use the left end points? Now, we still have our 8 rectangles, but instead of this first rectangle, instead of going to the right side and up, I'm going to go to the left side and up. And then I make this, right? And now this estimate's going to be too low, isn't it? What is it? 35.5, right? Or I could do something else. I could instead of going to the left or right, I could go right in the middle. So I could go and say, here's our 8 rectangles. Instead of using the right end point and going up and over, or the left and up and over, I just go right in the middle of the interval, go up and out. Does that make sense?
Yes, sir.
And what would that estimate be? 42.5. That's even better, right? So you might be saying, couldn't we become more efficient with this? It's not going to matter, okay? Because what is our ultimate goal? Our ultimate goal is to let the number of these become infinite. And when you let it become infinite, what happens to the width? Goes to this, right? Goes to 0, and basically the left endpoint, right endpoint, middle point, any point in there doesn't matter because it's all converging down to one point anyway. Does that make sense?
Yes.
Okay. So Let's see. We just did 8 rectangles, didn't we? How about let's do 100? Or no, I think this only goes to 70. Let's keep the same formula, but let's do 70 rectangles. Okay, 70 rectangles. Should I write out the area of rectangle 1 and do this for all 70? Hell no, I'm not doing that. In fact, I'm going to just go right to the summation because nothing's going to change in the summation except what? The end, where we're stopping, right? Where we're stopping. So I'm not even going to do that. I'm going to say that our new approximate area, let's call it double tilde just because it's fun to do 2 tildes. Our second attempt at this, I'm going to do the sum, sum k equals 1, but this time I'm going to do 70 rectangles, 1/2. Now, is the f of thing going to change? No. It's still that thing squared, which for us was what? 1, I forgot. Plus 1/2. Was it 1? No, it was 1 plus k. Yeah, you're right. 1 plus k, then plus a 4th k squared, right? Okay, so do y'all see nothing's changing except the 70? And so I'm going to wind up doing exactly what I just did. It's just my calculations are going to be different, aren't they? Like, because my common sum formulas, instead of stopping at 8, I'm going to stop at 70. You'll see that? Now, I don't want us to actually go through that because it'll take too much time. I'll just have the computer do it. If we do 70 rectangles, look at our approximate area. 42.02. Still not that great, right? Still not that great? So what would be the ideal thing? The ideal thing would be to do this. Not quite. Yes and no. Slap infinity on the sum, right? How about this? How about we ask ourselves this? What would the sum k equals 1 to n be? So instead of having 8 rectangles or 70 rectangles, let's have n rectangles. N, right? Then what would our formula become? So this is for n rectangles. We'd still have the half, right? And everything else would still be the same. Okay, now I want us to actually go through this. I know it's going to suck, but let's actually crank this out. All right, so let's see. Can I skip to this step first? Can I go here? Can I just go equals sum k equals 1 to n of 1/2 plus, I thought we had, oh yeah, plus 1/2 sum k equals 1 to n of k, and then plus 1/8 sum k equals 1 to n of k squared. Do y'all see that that is the same formula we've been using, but instead of 8 or 70, we're using n, yes? So this should be the formula for n rectangles. All right, what do we get from this first piece?
1/2 n.
1/2 n, yes? Half of n.
N squared plus 1 plus n over 2.
Well, you know what? Hold on. We have an issue. We have an issue. We need to rethink this. Yeah, that's our width of our rectangles, right? That's our width. Yeah, we'd have to change that. That wouldn't impact us if we had 70 up here, right? Well, no, I mean it would. We'd have to adjust it.
Yeah.
Okay, so.
If that was 70, if n was 70, it'd be 1 over 70.
Yeah, so if you go back and look at when we did 70, right? 70 rectangles. On that interval, how wide was the interval? How wide is it? The whole interval is 4, right? And we divide by how many rectangles? 70. That's how wide each one was, right? But the thing is, we could still compute it. We could still do it. It's just a constant would change. But here, how wide is each one? This is going to be different.
1 over n.
It would be for this. So let's come back. Let's come back to here, right here. We have to change that. So the total width of the interval is 4, right? But we're cutting it into n equal pieces. So we're going to go 4 over n. That's how wide each rectangle is. Do you all follow that or no?
Yes.
4 over n? Go ahead. You want me to go?
Okay, yeah, can you just repeat it one
So
more
remember when it was 8 rectangles, we said how wide is it? It's 4, and then we divided by 8, and that's where the 1/2 came from. Now we're saying our interval's still 4, but we're going to cut it into how many rectangles? N. N. That's how many rectangles I want to make. So I need to just take 4 and divide it by n. Okay? Yes? Okay, so the only thing here that changes is this should be 4 over n. And that is going to have an impact up here. So I've got to rewrite this. I'm having one of those weeks where I just want to go crawl into a cave.
Is it
Yes?
gonna change that part too? Could we use the width of,
We use the width in here, right?
yeah.
Okay. So I think what we need to do is, I think we should just back it completely up and just draw the picture over. I think that'll be the best bet for us.
At least that would get
Yeah. So let me ask you this: Do you want me to go through this particular example with n rectangles, or do you want to do an arbitrary function? I think, let's do this one. Let's do this one with n rectangles, and then we'll do an arbitrary one. All right. So we're still here. We're still here. We're trying to figure out the area under that curve if we use n rectangles. So I'll draw my picture up here. We're going to start at 1 and stop at 5. Go up like that. And then we're going to have n rectangles in here. We all agree that the width of each rectangle should be 4 over n. That's the width of the interval divided by how many rectangles we have. Okay, let's talk about the area of rectangle 1. Okay, so how wide is it? 4 over n. Okay, then we have to do times the height. So imagine here's our first rectangle. So what point are we at here? This is the big question mark. Where are we? Because we got to take that point and plug it into the function, don't we? So we want the function evaluated at 1 plus, so how much do we move over? That much, right? 4 over n. Just one jump, right? 4 over n? That's just one jump over. What would the area of the second rectangle be? Well, how wide is it? Still 4 over n times f of 1 plus, now this time we're going to jump how many? 2 of those, right? 2 of those 4 over n's. And then the next one should be that plus 3 of those jumps, yes? Okay, so what should we get when we get to the nth rectangle? Still 4 over n wide, right? F of 1 plus, how many jumps have we made? N of them. We've made n jumps. So n 4 over n's. And you can verify that the n's would cancel here and you would get 5, which is the right endpoint. Can we write that in sigma notation? We can, right? So the area, let's go triple tilde. That's just fun to me. Okay, because we're doing the third iteration of this. We did it with 8, we did it with 70. We needed to fix some things on 70, but for n, here it is. Sum k equals 1 to n. Okay, how wide was each one? 4 over n, and then f evaluated at 1 plus. So what's changing as we do these? This coefficient right here, 1, 2, and then 3, and then 4. So it's this thing, right? So it should be k times 4 over n. This is the thing that's changing, right? And now let's go ahead and square that. Let's figure out what that is, because we can use our function again, can't we? So I should probably do that over here. What would 1 plus, let me write it this way, 4k over n, that quantity squared be? So that's me using the squared function for that particular expression. So that means square that, so it's that times itself. So we should get 1 plus what?
1 plus 2k4, or 1 plus 2, 4,
8,
n.
yeah, 8k over n, and then plus 16k squared over n squared. So that should be what we get when we actually plug this into the function. And now I can come back up. You understand? Just FOIL that out? Okay. So now we're at sum k equals 1 to n of 4 over n. And then this became 1 plus 8k over n plus 16k squared over n squared. Okay, there we go. This is our formula that'll give us the area for n rectangles underneath the function x squared on the interval 1 to 5. Right? So let's see if we can use our common sum formulas to figure out what this is. All right? So now what I'll do is I'll distribute this through. So we get sum k equals 1 to n. Okay, so this times 1 is just 4 over n. Then when I go here to here, what do I get? 32k over n squared, and then plus 64k squared over n cubed. Now I know this looks messy, okay? This looks messy. However, the summation, the only thing that's changing is k. Would you all agree? Like n is fixed. Whatever it is, n rectangles, whether it be 8, 70, a billion, n is fixed, right? That means I can act like n is a constant in each of these. So look at what my next line is going to look like. That's just having one of those weeks. Too much going on. There we go. Okay, so what I did is I treated everything that didn't have k as a constant and pulled it out. So 32 over n squared, I split it into 3 separate sums, right? And then I left the 4 over n there because it's a constant. This right here, I pulled the 32 over n squared out, and here I pulled the 64 over n cubed out. And that was to kind of isolate these common sum formulas right here. And then this one I actually know also, right? Okay, so what would this first sum be? 4, because we're going to multiply n times 4 over n. I'll go ahead and write that down, n times 4 over n. It's going to become a 4. Okay, plus 32 over n squared times what? What does this sum become? N times n plus 1 over 2. Okay, plus 64 over n cubed times this one, which is n times n plus 1 times 2n plus 1 all over 6. I forgot squared? Yeah? Okay, let's clean it up. This is going to be 4 plus, okay, over on this one, 2 goes into here, what, 16 times? And then I'm actually going to put these together. What is this? N squared plus n? And then a 16. So 16n squared plus 16n over what? over n squared.
2n squared.
I put the 2 into the
Oh, sorry.
32, so 16. Do y'all agree with that next line? Okay, this one's going to be a little bit uglier. Remember, this right here is n squared plus n, right? That's what those two are. And then I can multiply it times this. So what would those two multiplied together be? 2n cubed plus n squared plus 2n squared, what? Plus n? Okay, so multiplying all that stuff up here together gives us that, which is really 2n cubed plus 3n squared plus n. Y'all following me? I'm just doing some algebra there.
Yeah.
And we still have a 64 in front of all those. So let's distribute that 64 through. So 64 times 2n cubed would be 128n cubed plus, what's 64 times 3?
192.
192 n squared, and then the last one 64n, right? And then all of that's divided by what? 6n cubed. I guess I could have reduced, right, by 2. I didn't. I'm okay. I'm just going to leave it. All right. What do y'all think? Aren't Riemann sums fun? Okay, so this gives you the area if you do n rectangles. So if I gave you an n right now, could you plug it in?
Yes.
Yeah, you could. You wouldn't want to, but you could. So now, go back to the idea, Hogan. You had this idea. You said, let's let n be infinite, right? Let's let n be infinite right now. Okay, at this point. So instead of putting infinity here, after I simplify this summation, now let's let n go to infinity. And what happens if you let n go to infinity? What do you get right here? On the top, where's the top headed? Infinity over infinity. Cal 1, that's an indeterminate form, right? Here, what do you get? Infinity over infinity, indeterminate form. L'Hopital's rule, I heard it, right? We can use L'Hopital's rule here. So now what we want to do is we want to not start over, but kind of start over. Okay, watch. Here's what I'm going to do. Okay, the true area. The true area should be A equals, now I'm going to leave a space here in front, sum k equals 1 to n of what we had before, 4 over n f of 1 plus k times 4 over n. That was where we kind of started everything off, didn't we? Okay, we want to find this, we want to find that, but when we're all done with all this, we're going to let n go to infinity, right? So I'm just going to put in here in front limit n goes to infinity of this. Okay? So we figure out what all this is algebraically, and then, that's this expression, then we let n go to infinity. Y'all ready? We're going to do it on that right now. Okay? So for this particular problem, this should be equal to the limit as n goes to infinity of that expression. 4 plus 16n squared plus 16n over n squared plus 128n cubed plus 192n squared plus 64n all over 6n cubed. All right, now when we do this limit, we apply L'Hopital's rule. So anytime we apply L'Hopital's rule, we either put like an L or an H above the equal sign. I always put L and circle it. So L'Hopital's rule here. Will L'Hopital's rule have any impact on the 4? No, so that's just 4. But this one, because it's infinity over infinity, you take derivative of the top and bottom separately. So what's the derivative of the top? 32n plus 16. What's derivative of the bottom? 2n. Okay, we'll come back to that. Plus, over here, derivative top and bottom separately. 360, 70, 384. 384 n squared plus 384 n plus 64 over 18 n squared. Okay, so now, if you let n go to infinity, same problem. You have infinity over infinity, infinity over infinity, L'Hopital again. Yep, keep doing it until it stops. So this is going to be equal to, by L'Hopital's rule, the limit as n goes to infinity of 4 plus, okay, L'Hopital on top and bottom here. 32 over 2. Okay, plus, now on this one, oh man, these numbers are starting to get big. 2 times 384, 768. 768n, right? Plus 384 over 30, what's that, 36n? Okay, we're going to need L'Hopital one more time. Right? One more time. So when we do L'Hopital one more time, we get 4 plus, what's that? 16 plus 768 over 36. I'm sure that reduces. But what is that? Pardon? It's okay, let's reduce it and keep it as a fraction. Okay, let's try and get that in lowest terms. What is it?
64 thirds.
64 thirds? Okay, so this is going to be 20, right? 20 plus 64 thirds, that's what you said when we reduce that fraction? So that means 12 goes into each of those, is that right? 12 goes in top and bottom? Okay with that? Okay, can we get a common denominator between those two to put them together?
4 over third.
So 3 on top and bottom here, so what do we get?
124.
124 over 3. That should be the exact area. Now, as a decimal, what is that? 41.33333333 repeated, which, as you can see here, is the actual area under the curve. Yeah? Yeah. And look, what happens if we change our interval? Instead of going from 1 to 5, we go from 2 to 6. We got to start over. Right? We got to start over. Yes.
Can I ask you a question?
Yeah.
So, I wasn't taught L'Hopital's rule.
Yeah.
So, like for the 4, right?
Uh-huh.
You just bring it along.
Yeah, because you only apply L'Hopital's rule to the limits that are of an indeterminate form, that have infinity over infinity or 0 over 0. Omar?
Will K always be 1?
Pardon?
Will K always be 1?
Will K always... In our Riemann sums, yes. Uh-huh. Yes.
What if you algebraically factor out n and then take the limit and then it will be like 1 over n approaches 0 is just 0. You still get the same answer, right?
Wait, if you algebraically did what? Factored out and like here, you mean?
Yeah.
Factored out and
All of them.
what do you want me to factor out?
So like cancel out n and then it's going to be 1 over, it's going to be 16 and 16 plus 16 over n.
Yes.
Which is going to be
Correct.
0.
So what you're doing is another method that doesn't require L'Hopital's rule. It's just, when you first learn infinity over infinity, the method is that you multiply out here by the highest power, 1 over the highest power of n. So yes, that would work. Okay, now, I'm just so much time. Riemann sums take up so much time. Okay, so look, I can only spend maybe 10 more minutes on this. So I'm going to go very quickly, all right?